Hey everyone, welcome to the fourth video on numerical methods. So in this video we're going to talk about a couple of improvements you can make to Euler's method, one being the Hume's method we talked a little bit about before, and another being adaptive methods, which I'll sort of go into in the actual video itself. They involve changing step size to accommodate for your bound being too big at certain points. All right, let's go ahead and jump on and just right into it. So the first thing I want to talk about is this Hume's method, or the improved Euler method as the book also likes to call it. And if you work out all the details, what you get is this sort of equation for your step process. So it tells us that the next step is determined by the previous step plus the function of a at the previous point and the function of a at the next point over 2 h times h. So basically what you would do is you would use normal Euler's method to predict what y plus 1 is going to be, then use this method to actually calculate what your next step is going to be. So use that predicted value to attempt to calculate your next step, and then just go through it a couple times and then move forward from there. Now, if you take this and you go through the Taylor series stuff we did last time, what you'll end up coming up with is that this is actually has local error of order h to the third. Basically what happens is that because you have both the tn and the n plus 1 sort of playing with each other, the h squared term also ends up canceling out. So the first term that actually appears in the difference between phi of tn plus 1 and yn plus 1 is the third order term, is the h cubed term, because the h squared term ends up bouncing out, canceling, and it goes away. So you have local error of order h to the third, which means by the same argument, the global error is of order h squared, which is one order better than we got for the normal Euler's method, right? Euler's method was only a first order approximation, which meant that if I halved my step size, my error only got cut down by a factor of 2. Whereas here, this improved method is order h squared. It's a second order method, which means that if I cut my step size in half, I should have a factor of a fourth applied to my error as well. So my error bound goes down by a factor of 4 when I cut my step size in half, instead of just going down by a factor of 2 when I cut my step size in half. So this is what I meant when I said in the first video that this method is a better method because it has a better order of convergence. Now the second thing you can do to improve methods is use what are called adaptive methods. Now what adaptive methods means is I'm not going to use a fixed step size. I'm going to change my step size based on some factors. So if I look at Euler's method, what did I get for my local error? My local error came out to be something like h squared over 2 times the second derivative at some point tn star, where tn star was between tn and tn plus 1. Right, that's what my local error looked like. Now, a way you could sort of try to compensate for this is I could change h based on what phi double prime looks like. So the idea of adaptive methods is make h smaller when phi double prime is bigger. I know it's a really, really vague sort of sense to throw out there, but if my second derivative gets really big, I can shrink h to reduce my local error at that point, and then keep going while phi double prime is really big. And then when phi double prime starts to flatten out again, I can take a little bit bigger steps. So I can attempt to keep local error constant by reducing h when phi double prime is large. Basically, since phi double prime is sort of measuring its concavity, it's measuring how fast the solution is pulling away from the tangent line, when it's going away really, really fast, I want to take really, really tiny steps, because really tiny steps will keep me closer to the curve overall than taking a big step and flying really far away from the curve. So the idea is that when the derivative gets really big, I want to take tinier steps to stay closer to my solution curve instead of taking a huge step and being farther away because I didn't notice that things were getting out of hand. This can be done. It doesn't really help improve the order of the method, but it gives you more stable results because you're less likely to be influenced by this constant being giant if you change h to compensate for the fact that it's getting big at certain points. In general, most computers will sort of have this already built in. You can have solvers do adaptive methods or just straight time step methods, depending on what you want to do. So most programs already have this sort of thing built in. It's also not too hard to build it on your own if you want to. You just have to take into account what this derivative looks like and then change h based on that as you step forward in time. So those are the main two ways I want to talk about in this video for how you set up these methods and what you can do to improve them. In the next video, we're going to talk about one method that is a fourth order method, so it's a lot more accurate and does converges a lot faster than these ones we've talked about, but it's also a lot more complicated, which you would expect in sort of a trade-off for getting a method that is that much better than anything else. And that's called the Runge-Kutta fourth order method. So we'll do that in the next video. Thanks a lot for watching, and I'll see you in that one.